Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. In this video, we'll learn about the basics of microphones, the primary tools to measure sound.
So let's get started. You may already know that microphones are what we use to measure acoustic pressure. The microphone that we commonly see day to day is called a condenser microphone. That's shown here at right. A condenser microphone uses a tensioned, polarized metallic diaphragm fixed above a backplate. So the diaphragm is tensed and fixed above this backplate. A prepolarized microphone is called an electret condenser mic, and we'll talk more about that in a moment. The small gap between the diaphragm and the backplate, due to the electrical charge between them, this creates a capacitance change when acoustic pressure causes vibrations of the diaphragm. So here we have our electret condenser microphone. This is a standard breadboard fitting that has the pins to be attached to a breadboard, 2 leads, and this would need some charge amplification. Let's take off this facing sheet to see what's underneath. If we do this, what we see is that this is simply a felt layer for protection that when pulled back reveals a shiny object underneath. This is our prepolarized condenser electret diaphragm. Here we have an electret condenser laboratory grade microphone. This is made by PCB Piezoelectronics. The model number is shown here, 130F20, and the serial number is shown here. A corresponding specification sheet was provided with this microphone for all of the specification details. Inside this case is a prepolarized microphone. This part at the very end, from my fingernail to the top, is the actual microphone. And this looks similar to our small PCB scale electret, although it has these side venting holes at the top. This part of the cartridge, which looks similar to a bullet, is called a preamplifier. It's used to minimize the signal conditioning required. The product information is also written along the side, along with the serial number. It says it's ICP, so it's a charge-based piezoelectric device. And this is a BNC jack that would be used to go to a signal conditioning and data acquisition system. The voltage difference that's associated with the capacitance change is then detected and converted through a sensitivity value to acoustic pressure. The most common microphone that is used to date is the electret condenser microphone. And this is the version of the condenser that has a prepolarized diaphragm so that there's no need for a separate external hardware for polarization. The electret was invented by James West and Gerhard Sessler at Bell Labs in 1962. It remains the most scalable microphone and most widely used microphone to date, being used billions of times per year from everything from cell phones to laptops to even laboratory microphones. Microphone sensitivity is the value that helps us convert the voltage change that's recorded to pressure in pascals. This metric is sensitivity. It's reported as pascals per volt, or on a specification sheet like we see at the right, sometimes manufacturers will report it as millivolts per pascal, which of course would need to be inverted before multiplying the value by the measured voltage. Sometimes a conversion is used to report the sensitivity as decibels with respect or reference to 1 volt per pascal. If you want to convert the sensitivity value in millivolts per pascal to the dB value, you use this equation here. It's 20 log 10, the sensitivity divided by 1000. Depending on the manufacturer of the microphone, you might see both of these sensitivities reported, or you might just see one. And if they report only one, the dB variant, is common. Microphones also have a frequency response. Ideally, we want it to be flat. What do we mean by this? Well, microphones that you buy for laboratory purposes or even off the shelf will likely come with a calibration certificate and a frequency response plot. And we see the response plot here at the bottom right. We see that at the lowest frequency, around 20 hertz, the response is just around a value of 1. So the microphone provides a measured voltage that is very similar or almost identical to the actual acoustic pressure. Then at the high end, at 20 kilohertz, we see the frequency is a little bit less than 1 right here, where the red line is. And in general, the microphone response is mostly flat. This is a decibel scale. So we see only about 3 decibels, maybe 3 or 4 decibels peak to peak at the high end of the frequency response for this microphone. Ideally, we want this to be flat. And a specification sheet will often indicate the frequencies over which such and such error is reported. So over plus or minus 2 decibels in frequency amplitude deviation, we have accurate recordings from 20 to 10,000 hertz. And if we are comfortable with a greater amount of error, then our microphone can measure even subsonic down to 10 hertz and up to 20,000 hertz. It is also important to recognize that the microphone response doesn't stop at the frequencies that are shown on these charts. In general, you can use a sonic microphone even to measure ultrasound, in other words, frequencies above 20 kilohertz. The implication, though, is that at ultrasonic frequencies, the sensitivity might roll off. We don't know it. It's not reported from the manufacturer. We could calibrate it, of course, but you can still measure ultrasound with a sonic microphone, but be wary about converting that to actual pascals and actual sound pressure levels, since we don't really know the sensitivity in that frequency range. And another important characteristic of microphones is the dynamic range. It's the range difference between the SPL at the highest and lowest SPL values that can be recorded without distortion. Sometimes manufacturers actually indicate, for instance, 3% distortion limit for this dynamic range, which is 122 dBs, which, if you recall, 120 decibels is the difference between the threshold of hearing to instantaneous hearing loss. So we see, though, that the lowest values that could be reported are in the 20s of dBs, where the inherent noise is. For the A-weighted and the linear up here, 29 dBs. So we could add 122 to 29, and that would give the measurement range in specific absolute values for the lowest and highest SPLs that can be recorded. The dynamic range is important because if we choose a microphone that has an insufficient dynamic range, we'll get clipping. And clipping is the phenomena where we overdo the voltage on the output. In other words, the microphone diaphragm is displacing so much, it's either acting non-linearly or it's mechanically contacting the backplate and, of course, shorting out. You often get extraneous or unusual voltage readings from a microphone that's clipping. Laboratory microphones will often have dynamic range of 120 decibels or more. Cell phone microphones, in other words, day-to-day communication microphones, will often have dynamic ranges of 60 decibels or maybe a little bit more. Modern cell phone microphones have improved in quality. But this is evidence that they're intended for low-cost, high-volume production purposes. Microphone size determines many of these characteristics. Laboratory microphone diaphragms will be available in diameters 1/8, 1/4, 1/2, and 1 inch. What's the difference between these diameters? Well, microphones with larger diameters can measure lower frequencies and lower sound levels, and they're capable of doing so for the same reason. They have more compliance in the tensioned diaphragm. In other words, there's more capability of the diaphragm to displace due to large fluid particle displacements, which are proportional to lower frequencies and lower sound levels. Microphones with smaller diameters measure higher frequency sound but have less dynamic range. For instance, microphones that measure ultrasound commonly come in the 1/8 diameter size range in order to measure the very short wavelengths of sound. So let's summarize what we've learned. Microphones measure acoustic pressure and the output of voltage. We use a sensitivity that's calibrated for each mic to relate the registered voltage to an acoustic pressure. Frequency response and dynamic range are large for high-quality microphones. Simple mics, for instance those we will find in cell phones, they have good frequency responses and dynamic range, but they are optimized for voice signals and communication. In laboratories, the microphone size is an important factor for selection. A good laboratory will have a variety of microphone sizes.
That's it for this video. Now that we know all about the fundamentals of microphones, in the next video we'll be introduced to a wide variety of microphones that are used in many engineering practices.